Hello, everyone. I'm a PhD student from the University of Skövde in Sweden. My presentation is entitled Evaluating Data Inconsistency of Open Source Vulnerability Repositories. Modern security practices promote quantitative methods supported by online cybersecurity data sources that can be classified into 5 semantically annotated categories. For example, vulnerability repositories identify and describe recorded vulnerability instances. System repositories provide system configuration information. Threat, attack, and remediation repositories describe threat tactics, attack instances, and suggested patches separately. Research efforts are seen in cyber threat intelligence sharing, which aims to provide prioritization insights and enhance cybersecurity awareness. Such security practices involve checking latest vulnerability reports from accessible cybersecurity sources. There also exist various commercialized products that are based on data feeds from these public data sources. Data quality of the cybersecurity data source is therefore a key aspect to investigate. The issue is that diverse vulnerability reporting sources may give inconsistent information. For instance, inconsistent severity scores exist for the same vulnerability instance. In this paper, we aim to investigate the impact of data inconsistencies in open source vulnerability repositories for real-world IT and OT infrastructures. The research questions in this paper are twofold. The first question is, do multiple open public cybersecurity data sources provide consistent information regarding to vulnerability analysis? The second question is how to evaluate the impact of data inconsistencies of these cybersecurity repositories. So, what is data inconsistency? It refers to data values in one dataset not being consistent with values in another dataset. Consistency analysis mainly includes 5 contexts, namely record level, cross-record, temporal, application or business level, and reasonableness level consistency. In this paper, we mainly consider record level and cross-record data inconsistencies. To better quantify data inconsistency analysis, we define the listed parameters. Using these parameters, each vulnerability instance can be expressed as a vector of attributes. Record level inconsistency exists between vulnerability attributes. It is seen where multiple names are provided to represent the same entity, such as vendor names, vendor product names, and vulnerable product versions. Cross-record inconsistency exists between vulnerability reports that have the same CV IDs, but are extracted from different data sources. It indicates scenarios where the same attributes, such as vulnerability severity scores, publication dates, and vulnerable products are conflicting, or where multiple attributes indicate contradicting vulnerability characteristics. We query related vulnerability instances from 3 cybersecurity data sources. NVD builds upon information included in CVE entries to provide enhanced information for each entry. Besides, we deployed vendor data as an additional source to add the perspective of manufacturers. We focus on 6 attribute assets for vulnerability analysis that are available in a minimum of 2 data sources, namely description, applicable product, version range, CVSS score, impact elements, and weakness type. The methodology for data inconsistency analysis is composed of 4 steps. Firstly, we collect system configuration information and component details. We then write the import filter to translate component information into query tags. Secondly, the translated tags are used in Python-based queries to extract component-based vulnerability instances. Here we take the union of all retrieved vulnerability reports. Thirdly, we extract attributes for each vulnerability instance. We employ two approaches to obtain these values. We directly parse NVD JSON files for the targeted attributes. We also build a named entity recognition module to extract other attributes from the description. Lastly, we compare the attribute sets of each vulnerability instance set to diagnose inconsistencies. We conducted a case study on vulnerability analysis of the IT and OT systems of a company in Sweden. The investigated IT system is composed of a data center, an application layer, and a network layer. In data center, hardware components like physical servers integrate with operating system and manage PC storage. For example, a hypervisor host deploys and serves virtual systems, which provides an abstraction layer for virtualization. The application layer includes a configuration of 3 system packages supported by hypervisors, namely IoT or Internet of Things system, customer management system, and control system. On the other hand, physical servers in the data center are connected to switches through fibers. The network layer represents the wireless connections of the IT network. These switches are further connected to the OT servers. This table lists the amount of vulnerabilities found for each subsystem from CVE, NVD, and vendors separately. The investigated system contains components provided by 18 different vendors. Among them, 10 vendors provide specific sections for security adversaries. On average, if we take the intersection set, the customer management system has the highest number of vulnerability instances per component. In contrast, the operating system has the least amount of vulnerability instances per component. Then we focus on cross-record data inconsistency analysis, especially between NVD and vendor adversaries. The communication network system has the top data inconsistency rate among the 6 investigated subsystems, which is then followed by the OT system. For example, in the OT system, the open platform communication component has the highest amount of vulnerabilities when considering only NVD entries. When taking into consideration only the vendor entries, however, the protection and control component contributes the most vulnerabilities. In the IoT system, for example, the database toolset component has the most vulnerabilities in the operating system when considering only the vendor entries. When accounting only NVD entries, the most vulnerable component in the operating system is the directory component. Similarly, the remaining 4 system servers have different rankings of the most vulnerable component after considering data inconsistencies. We examined the CVSS version 2 base scores of our investigated systems. Vulnerabilities from NVD entries contribute more instances with higher severity scores, meaning equal or larger than 7. This is especially true for network and control system related vulnerability instances. We also measured the influence of inconsistent vulnerabilities on exploitability and impact levels of the whole investigated system. Only accounting for NVD entries, these vulnerability instances may lead cybersecurity analyzers to pay closer attention to threats with local path-based attacks, low access complexity, and no authentication requirement. Meanwhile, only accounting for NVD entries, the analysis results suggest that our investigated system is suffer from a higher impact on confidentiality, integrity, and availability. We then correlated the extracted vulnerabilities with weakness enumerations, or CWE, to explore measure weakness of each investigated system. The top 3 weaknesses with the highest occurrence frequencies are changed or revised with rankings when considering different data sources. For example, the most frequently appeared weakness of network is inflow validation for only considering NVD entries, which is changed to exposure of sensitive information to an unauthorized actor for only considering vendor entries. We interviewed 5 cybersecurity experts to validate the case study result. 3 of them are employed in the investigated organization to ensure the confidentiality of the study system. These 3 experts also have in-depth knowledge of the system status. The interviews focus on 2 questions. First, does this case study deliver a significant number of reports for the investigated system and cover unknown weaknesses that feed the gap of vulnerability management? So the second question is, how is the impact of the identified data inconsistencies in cybersecurity decision-making, especially if the vulnerability analysis results can be misleading in patching priority? Here we summarize the interview results. First, we confirm that a significant number of vulnerability reports are found using public vulnerability repositories. The vulnerability analysis results indicate some weaknesses that the 3 technicians are not aware of. One interesting example refers to the Office application component that contributes a large amount of vulnerability instances in the customer management system. Still, some known vulnerabilities from those 3 technicians in the OT system cannot be found using online cybersecurity data source and are not published by the vendor. The lack of OT vulnerability records also indicates the incompleteness of online cybersecurity data source. Lastly, data inconsistencies are not uncommon. These data inconsistencies bring a higher level of uncertainty in cybersecurity decision-making with amendments in the radius of measure weakness and threat types. We conclude that our case study is conducted in a semi-automated manner. Improving the level of automation supports a timely vulnerability analysis lifecycle. We did not investigate the root cause of the inconsistencies, like which vulnerability instance was created first, when it was updated, and so forth. Our study does, however, indicate that better workflows should be installed to synchronize and correct vulnerability instances in the public and vendor repositories. Some of the key insights are systematic integration of vulnerability instances into a kind of data warehouse offers opportunity to detect inconsistencies and refer them to the maintainers of the original source. The case study also showed that the number of inconsistencies could largely differ depending on the type of software component. Furthermore, vulnerabilities are reported in various standards, which increase difficulty of vulnerability-related provisioning and sharing. Vulnerability reporting standardization is one way to enhance the quality of shared cyber threat intelligence. Thank you. Any question, please?